All right, everyone. Today, we're going to put on our electrical engineering hats. We're going to follow a piece of critical power electronics equipment all the way from the blueprint to the real world, from a clean schematic to a humming, working piece of hardware. This is where the neat and tidy theory we learned gets, well, a little messy.
So here's our game plan. First, we'll look at the design blueprint, the core architecture. Then we're going to get our hands dirty with the math that engineers absolutely have to know to analyze these systems. And finally, we'll tackle the unexpected and sometimes pretty tricky side effects that pop up when a design meets reality. Let's jump right in. Okay, first up, the design blueprint. Look, before a single component is soldered, there has to be a solid plan. We're going to break down the anatomy of a power system that, and I'm not exaggerating, keeps our modern world running. And our case study for today is the uninterruptible power supply. You've probably heard it called a UPS. Its job sounds simple, but it's incredibly important. Deliver perfectly clean, rock-solid power to something critical. We're talking server farms, hospital equipment, even if the power from the grid is flickering or goes out completely. Okay, so let's trace the path of the electricity here. AC power comes in from the wall, and boom, step one, the rectifier turns it into stable DC. Now, this DC power is doing two things at once. It's charging up the battery, that's our safety net, and it's feeding the inverter. The inverter's whole purpose in life is to take that DC and craft a brand new, perfect AC sine wave for our sensitive load. And that last piece, the bypass switch, that's the engineer's ultimate OO button. If anything in the UPS fails, it instantly switches the load back to the main power. It's called a double conversion system, and it is the gold standard.
All right, we've got the design. Now let's talk about analysis. The voltages and currents inside a UPS are not the pretty clean sine waves you see in your intro textbooks. No way. Because of all the high-speed switching going on, the waveforms are chopped up, pulsed. They look pretty gnarly, to be honest.
So this brings up a huge measurement problem. I mean, how do you put a single number on a waveform that looks like a series of jagged mountains? You can't just use the peak value, right? A super short spike doesn't really tell you much about the actual power being delivered over time. We need a smarter way to do this.
And the answer, the elegant solution to this problem, is something called the root mean square value, or RMS. The easiest way to think about it is as the effective heating power. It basically asks what DC voltage would produce the same amount of heat in a resistor. It's an absolutely brilliant tool that gives us, one, consistent number to describe the true power of any waveform, no matter how weird it looks.
Now, the great thing is, you don't have to derive this from scratch every single time. For the most common shapes you'll see in power electronics, sinusoids, rectangular pulses, triangular waves, engineers have already figured out the formulas. This table, this is part of the essential toolkit for any power engineer. It's how you do real-world analysis.
And this slide right here really sums it all up. On the left, you've got the ideal world of the textbook. On the right, you've got the complex, messy reality inside our UPS. RMS is the mathematical bridge, the essential translator that lets us connect those two worlds and do meaningful, accurate engineering.
And now for our final section. This is where things get really interesting and often really tricky. A design isn't done just because it works on paper or on a lab bench. It has to work out in the world. And all that high-speed switching, well, it doesn't just stay inside the box. It creates what we call peripheral effects. And listen, we're not talking about just a little bit of buzzing. These are serious problems. Imagine the heavy floor tiles in a data center slowly vibrating loose over time. Or think about sensitive medical equipment in a hospital getting garbage readings because of electrical noise from a power supply down the hall. These are real-world headaches engineers have to solve.
So these effects show up in a few different ways. You've got the stuff you can hear and feel, the acoustic hum, the physical vibrations. And then there's the one you can't see, which is often the most problematic, electromagnetic interference, or EMI. This is basically high-frequency radio noise that radiates out from the device and can mess with just about any other piece of electronics nearby.
So, what do we do about all this? We can't just ignore it. And here's the thing, you can't totally eliminate these effects. That's a battle against physics you're never going to win. But you absolutely can manage them, suppress them, and contain them. So, how's that done? Well, engineers tackle this with a multi-layered defense, kind of like a castle. First, you put filters on the input and the output. Think of them as bouncers at a club, letting the good power through and blocking all the electrical noise. Second, you can actually program the control system to switch in a quieter way. And finally, for whatever noise is left, you use physical shielding, basically putting the noisy parts inside a metal box to trap the EMI.
So, if there's one thing you take away from this today, It's this. Real engineering is not a straight line. It's a cycle. You design the system with the blueprint, you analyze it with tools like RMS to see what's really happening, and then you refine the design to deal with all those messy, real-world side effects. Design, analyze, refine. It's a loop. And this leaves us with a pretty fascinating question for the future, right? As we keep pushing to make everything smaller, faster, more powerful, these side effects don't just get a little worse, they can get exponentially harder to deal with. Figuring out how to manage them is one of the biggest challenges for the next generation of power engineers. Thank you for joining this explainer.